Hello everyone, it's May the 23rd. Okay, first one, max subsequent score, 2542. Have I done this before? I have done this before. You're given two zero-indexed integer arrays, nums1, nums2, of equal length, and a positive integer k. You must choose a subsequence of indices from nums1 of length k. For chosen indices, your score is defined as the sum of the selected elements from nums1 multiplied with the minimum of the selected elements of num2. It can be defined as simply as this times this. Return the maximum possible score. So basically we want to choose k numbers from nums1 and we want to find the sum, and we want to choose the k values in nums2, find its minimum, and we want their product to be the maximum. A subsequence is a set that can be derived from a set by deleting some or no element. So a subsequence, we have to keep the original order, right? But we can choose anything. Okay, we can choose indices 0, 1, 2. Okay. I don't remember this at all, which is good, right? It's like new problem. Okay, so the indices you choose will be the same for the first and for the second one, right? But, oh, it doesn't really matter. For choosing indices, yeah, it doesn't matter. You can sort them. It's just if you sort them, they have to be realigned the same way. Okay. So what do you say? Well, what do I say? What do I say? The maximum possible scores. All right, if I sort nums1, right? If I sort it, then I have the maximum sum, right? I have a maximum sum. And maybe that is the way to go. Hold on, here's what I'm thinking, right? We will have the maximum sum if I sort. So it will be 1, 2, 3, and 3. And of course, nums2, 1 doesn't change, so 2 doesn't change position. But 4 needs to come here, and then 1 and 3, right? So we have this. And in here, we have the largest sum, the second largest sum, right? The k equals 3, so this is the largest sum. This is the second largest sum. Not necessarily. This is the largest sum. This is the second largest sum. This and this and this is the second largest sum. And then we'll have these two, and then this. So if we do the largest sum, will be 2 plus 3 plus 3, right? Will be 8. And it will take the smallest among these. So 8 times 1 is going to be 8. That's apparently not right. And then or actually it's not quite easy to find. Right? If we do this, that's also 1. So if we do, I think it's this, this, and this, right? The minimum is 2, and this 1 plus 3 is 6 times 2 equals 12. K. I want to find a K. Okay. And let's try sorting nums 2. How about that? 1, 2, 3, 4, right? So if I sort nums 2, nums 1, 1, so it'll be 3. 2 will be 1. 3 doesn't change. 4 doesn't change. So that will be this, okay? So now we sort this. And the minimum, the largest minimum is this value. The largest minimum is this value, right? No matter how you pick, this is the largest minimum. And of course you can have this, you can get smaller. So okay, if I say this, that means we'll have to choose this. Then we shall choose 2 values that's the largest, which is this and this. Oh, I cannot choose this because this is 1. So we need to choose 2 large values. The largest values on the right hand side. The largest value on the right hand side. Oh, we only have 3 and 2. That might work, right? We sort nums 2. We find the k smallest, a k largest value. That's the biggest, the smallest value. And then we just need to find the k biggest value on the right hand side. The k biggest value on the right hand side. We actually just solved this problem yesterday. The k biggest value on the right hand side. We can just sort it, put the k biggest into it, and if the new value is smaller, we don't. If it's bigger, we put it in. All right? In fact, yeah, that's, and then we just, from this going down. Yep, I think this will work. So it's like yesterday's problem is a preparation for today. It didn't show up. Hold on, I have something I need to deal with. Okay. Let's do this. So, first things first, we'll have to sort nums 2. Sorted nums 2 shall equal to sorted for I and enumerate nums 2 and n and I. Okay. Then we need to say arranged nums 1 shall equal to for I for ni in sorted nums 2 nums 1 I. All right, we set these two up. Then we are going to we need a heap for the heap q. So heap shall equal to we want a min heap, right? We want a min heap. So what we need to do is for I in range n equals len nums 1, doesn't matter. For I in range n minus k. Okay, the first one, yeah, all the way to n. This is going to be sorted nums 2 I 0. Okay, this is a heap. And S2, no, that's not right. That's oopsie doozy. We got it wrong. It has to be, no, that's not right. Heap, I just go heap. Heap equals to this. We're gonna prepare the heap, which is to put whatever on nums 1, right? We need to put the k largest into the heap from num 1, right? So what we can do is just say for I in range n minus k, right? N minus k is the kth. Let's see here. What's this is the kth, right? So k minus 3. So k minus 1, n minus 1, n minus 2, n minus 3. Yeah. So that's the start. So it's on this all the way to the start. All right. So we have a res equal to 0. Okay. So now what we need to do is to decide on a heap. Okay. So we need a S1. Okay. Then we shall say while heap is smaller, then we need to keep add, right? Keep adding. You know what? I don't know. Let's get a heap first. Yeah, let's get a heap ready first. We can say while for no. We want to get all of them in and then just for I in range. Okay, this is to put nums 1, so n minus k all the way to n. Okay, so we shall say if len heap is smaller than k, then heap q dot heap push heap nums arranged nums 1 I. Right, so we kind of just keep adding to it. Then S1 we can do at the end. Else, if the length is already k, then we say elif arranged nums 1 I. If it's larger than heap 0, then heap q dot heap push pop heap arranged nums I. Right, and we just keep going through until we're done. So this is to prepare the heap, right? Prepare the heap. And then S1 shall equal to sum heap, right? Now we have this is a case. So we definitely Oh, I don't even need to. I just need to push them in. This one never happened because I only have k. Ah, that is correct. It shall be sufficient. S1 equal to sum. Okay, so that's what is done. Now, what we're gonna do here is say, we start from the first one coming in, right? The first one coming in, and we'll decide whether it's good or not. No, we don't decide. We compute it first. Okay? We compute it first, but then we have to do another round of computation, which I don't really like. So what if we just... Because I'm at this. S1 is already everything. Right? I think it'll be wiser that we do not have everything. Or it's okay. It's okay. Okay, it's okay. So we'll always push, right? We'll always push, or we check, right? We'll check. So we'll say if arrange nums I, if this is larger than heap 0, then popped, then S1 shall minus equal to heap q dot heap pop heap, right? And then heap q dot heap push arrange nums I, and S1 plus equal to arrange nums 1I. So this is the handle, right? To handle. And if it's smaller, then we don't have to worry. No, if it's smaller, we still have to worry. No, we still have to worry. Hold on. What he's saying is, if we have something, right? Because we want to take this, so we want to discard the smallest value here, right? So we can including this. So if this is smaller, so we need to discard one of this, the smallest, to including this, okay? If it's bigger, then we just include it. If it's smaller, then, interesting. If the current one is bigger, we definitely want the current one, right? And then we say res shall equal to maximum res S1 times sort nums 2 I 0. Else, okay, if the current one is smaller equal to heap 0, right? If it's smaller, then we don't want to do anything, but we want to say S1 need to minus heap 0, because we're going to take the smallest away, plus arranged nums 1, right? We need to add this because we're selecting the current one. So this is my S1, and then multiplied by this. And then at the end, we'll return res. Okay, let's see. $12. $30. What do you think? I don't know. Oh shoot. Nums 1, nums 2, k. Max score, nums 1, nums 2, and k. Heap expected 2 arguments. Heap dot heap push. I forgot a heap. Okay, these two pass. Do we have another example? Yes, we do. K have to be 1. Just give this a shot. Okay, give this a round. Let's see how we go. Wrong answer. Terrible. Previously, just 3 months ago, I was able to do it in one shot. Dear me, man. Expected 5. What the hell happened, man? I don't know. How did you get an 8 anyway? Anyway, 1, 4, 3, 1, right? So how'd you do this? 1, 4, 3, 1. So I sort 1 and 3. So this will be 4 and 1, right? And K is 2. So the second small, so it has to be 1. And then 4 plus 1. How did you get to 8? There's no 8. There is no 8, man. What the hell? Arrange nums 1. Sorted nums 2. 1, 3, 4, 1. That is correct. S1 is 5. That is also correct. And is 0. That's also correct. Arranged nums 1. Right? Arranged nums 1 is 4. Is it larger than heap? What's heap? Heap shall have just 4 and 1. Yeah. Arranged nums. Oh. Okay, I know why. Yeah, that's the problem. Okay, so we don't do rest here. Yeah, I thought we can cheat our way through this, but apparently we cannot. S1 times sorted nums 2, m minus k, 0, and minus 1. There we go. Unfortunate. That is a very unfortunate mistake. Very costly too, man. This shall be right. There we go. Yeah, that's just, how should I put it? I was trying to not do this, you know, I was trying not to do this, but yeah, it turns out it's not the right approach. You shall handle the first one, right? First one, handle the outside, which is fine. Sort nums 2 and rearrange nums 1 accordingly. We find the largest, smallest, find the kth largest value in nums 2, which serves as the largest, smallest value, right? Largest, smallest value in any chosen k values. Then we can use a heap, right? Then we can we then put the last k values, right? The last k values of nums 1 of rearranged nums 1 into a heap. And each time we move the pointer on nums 2 leftward, right? We check whether the corresponding value in nums1 is larger than the top of the heap, right? If it is larger, we swap that larger value in such that we ensure that the heap always holds the largest k values in nums1 so far. If it is not larger, we do not swap, but we still need to take it, right, to compute the current score. This means we have to temporarily deduct the smallest value in the heap from the sum of nums1 and add the smaller value. Because we have to add current nums1 value. Yep, O n log n. I believe that was the same solution as I had. Maybe we can take a look. This is the original sorted, reordered heap J S this while J new S. I do this. I always minus and then plus the current. If this is larger than, then we will add it to it. We'll pop and add. And then this as equal to S. Yeah, it's exactly the same idea. Implemented slightly differently. Oh, jeez, man. Didn't realize this. Yep, you can zip them. Yeah, still didn't improve, huh? We solve it using exactly the same idea, but we can zip nums1 and nums2 and build the heap along the way. For BA, for N2, N1, and zip and sorted, zip nums2, nums1, reverse equals to true, right? And we need a res equals s1 equals 0, okay? So we say if len heap is smaller than k, heap q dot heap push heap n2, now n1 s1 plus equal to n1, else, so we have k, so res equals next one smaller, then we do this, right? And then if it's equal to k, right? If len heap is equal to k, then well, once it come out, it's already equal to k, right? So we can say else it's equal to k. Then we have the current value if it's equal to k, which means S1, and we can how do we handle the transition? I have N1 and N2. Then what? I say it has to be already equal to the order. Right, we keep pushing, so you grow. So at a certain time, it grow to n. And s we add it to a certain value. And then for the next round comes in. But how do we calculate the current round? I mean, we can handle it here, right? We can add here. We say if it's equal to k, then we do some stuff, right? And otherwise, we'll, yeah, but it will be, we can say like if len heap is equal to k, because I want to calculate the first one. Then rest shall equal to s1 times n2, right? And here I can just say else. Then else will have two ways, right? We will be like if n1 is smaller, is larger than heap 0, then heap q s1 minus equal to heap q dot heap pop heap q dot heap push heap n1 s1 plus equal to n1 and rest equals maximum rest s1 times n1 n2 else s1 minus heap 0 plus n1 times n2 and we'll return rest. But that's not what I did. Oh, it is what I did. But I just did if. What if it's smaller? Oh, are you saying you don't consider this situation? Huh, if it's smaller, if the current n is smaller than the largest, which means the total sum on the top will be smaller than before. And on the bottom will not be bigger than before. That's why we can ignore it. Ah, makes sense. That makes sense. So we don't have to worry about this else condition. Also, know that we don't have to consider the condition where n1 is smaller or equal to heap 0. Because if that happens, S1 will always be smaller than before. Always S1 and N2 will not be bigger than before, which means their product cannot be the max, cannot be the result, cannot be bigger. See, that is the important insight. So this else is unnecessary, but it's okay. That is the right way to do it. But I did the same way here. The pop and push. Luck. That's exactly the same solution as I did last time. Okay, let's take a peek at this. Priority queue. Yeah, see this one. Uh-huh. 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 Yep, if it's top K. Yep, if it's top K, top something, there is a high chance that we're looking at a heap. All right, finally, let's transition to the last one of this smallest missing non-negative integer after operation. You're given a zero-indexed integer array, nums, and an integer value. In one operation, you can add or subtract value from any element of nums. For example, if nums 1, 2, 3, value is 2, you can choose to subtract num from it. Become, okay, the MEX, minimum excluded. The minimum excluded of an array is the smallest missing non-negative integer in it. For example, the minimum excluded is 0, while the minimum of this is 2. But the maximum minimum excluded after applying the mentioned operation any number of times. Okay, so you are adding. No, you're a minus, right? Or you can add or subtract. You can add or subtract from any element. So in this case, we want to find the maximum the non-negative, the minimum excluded. So we want to achieve 0, 1, 2, 3. Right? If you don't have 0, then it will always be 0. So you want to do 0, 1, 2, 3. You want to do 0, 1, 2, 3 all the way to the end. So that's what we want, right? So in here, if I have a negative value, then we want to turn it into a 0. And then we have 1, so we need a 2. But we don't have a 2. We have a 2. 7 can become a 2. We need a 3. 13 can become a 3. We need a 4. Well, if we need a 4, then this cannot be 4. So to make a 4, right, we need a 9. or a -1. We don't have any, so that's it. So the answer is 4. So for this one, 7. We need a 0. We have a 0. We need a 1. We have 1. We need a 2. So with 2, we need a 5 or 9. We don't have either, so that's going to be a 2. So basically, we have this, right? We have this, and we have a value. We want to ask the question, can we get a 0? How can we get a 0? Well, we need some value that mod this equals 0, right? Then you can get a 0. Or of course we check if a 0 is already in there, right? And then we want a 1. Then how can we do this fast? We can mod, right? Mod 0, mod 1, mod 2, mod 3, mod 5, mod 5. We have all the mods, right? And if we group everything by the mods, then what's going to happen? Then we want a 0. So we look for mod 0. We say, does it exist? Oh, you can also have, yeah, mod 0. You can also do mod. You can also get value as well. 2 times value, 3 times value. You can always do that. Wait, hold on. Python's mod is always, oh, it doesn't really matter. Negative, positive doesn't matter because you can go both ways. So we can just do absolute value, right? We can do absolute value mod 5. And I just want to confirm 0 mod anything is always going to be 0. Yeah. So I get a mod, right? Then what? Okay, actually, let's write it out. Here's what I think, right? So I have value 1, -10, 7, 13, 6, and 8. And my value is equal to 7. So I say mod 0, we have 7. In fact, we might be getting a counter. Mod 1, we have 1, 8, right? Mod 2, we have nothing. Oh, maybe that's it. Mod 2 is nothing, which means you cannot get mod 2. Okay. Yeah. Interesting. Mod 3, we have -10. We have a 1. Right? Actually, we can turn everything into positive first, so we don't really care. I'll just say 10. Mod 2 is nothing. None of them is mod 2. Mod 4. None of them is mod 4. Mod 5. Yeah, so basically we do this, right? Whoever is first. Now we have a situation where we have everything is fit all the way to mod 6, right? Everything is fit. Then what? Then we just need to see how many do we have, because each one can handle one of them, right? Let's say if I have 2 7s, then we can handle a 0. We can handle a 7, right? We can handle both. So now the question is, we check, right? Like this has 2. So this can handle, so this we have 1, we can handle 0. This has 2, we can handle 1 or 8, right? We have 2, we can handle 1 or 8. This we can handle, like we handle 3, we handle 2, and so basically we can have an array, right? So 0 we can handle, 1 we can handle, 8 we can handle, right? So like this, and then keep going, and then we just this seems to be reasonable. This seems to be reasonable, right? This seems to be reasonable. Ooh, how big are you going to be? The array. The array is going to be big. No, we're not doing array because we never know the size of the array. I think I'm just going to do from collections import, we need a counter. Yeah, I think a counter it is. And we're gonna say rem counter for any nums. No. Counter for any nums. Rem counter n abs n mod value dear God. So that, and then abs n plus equal 1. Okay. Then we need to have a, what are we going to have? We are going to have a value. Man, madre mia. We are going to have a exists. Okay, we do a counter. And we say for, oh my goodness, I equal to 0. How true? While true, what do we do? Well, we shall actually go through the whole thing first. Let me think. We go through the whole value first. Yeah, we'll go through the whole value first. So this is like for I in range value, right? Because this we can actually check the RAM counter, the RAM counter. So we first set it, right? We first set it, and because RAM counter, actually we don't even need to know. A counter will be sufficient because I don't really care which one causing you, because they are all the same. So I just need to do this. This is sufficient, right? Then what I need to do is I say, because I have that many values, right? That many values. Then it's just from I, right? And I plus value, and I plus value times 2, I plus value times 3, right? So we can say for j in RAM counter I exists value I plus value times j equal to 1, right? Exists. So initial is 0, right? And then j initial is 0, so 0 exists. And if we have more, then we can add 1 time value, 2 time value, all the way to what do we have? And now we have 1. All right, well, how can I do 1? Can do 2, I can do 1, can do value times 1 plus 1, value times 2 plus 1, yeah. So after we handle all this, we say if not exists I, now we return I, right? If after all these we haven't returned, that means we hit everything. Then we just say I equals value, right? And then while true, if not exists I, return I. Otherwise, I plus equal 1. It will return, but let's hope it doesn't. Performance is not too bad. Nums value. Find int is not iterable. Of course it's not, because it has to be range. All right. Let's see. What do we say? Wrong answer. Interesting. I don't know. These days I just kept getting wrong answer. Expected 2. Why did I get 1? Let's print a RAM counter. 0 and 3. What did I get? Answer is 2. You can get 1. Oh, dude. Damn. So I should not do ABS. Wait, I do not do ABS? What is this mod 5? Oh, it is 0. Huh. Yep. Do not do ABS. Then you're right. Gosh. Use a counter to find the total number of values in nums that share the same remainder one mod value. Then these numbers can form r plus value, r plus 2 times value, right? We use a set to record what values can be formed, what values can be formed. Then the first value missing in this set is the answer. I just realized I just need a set. I don't know. I thought it's the other way around. I not in exists, right? If I not in exists, that I think it can significantly improve the performance, because a set is a much easier data structure than that's all right. N. Oh. Yeah, there's still N because we only handle that many. Yeah, that's O(n) times value. No. You only have N. You just did all N. Oh, that's O(n) plus whatever the thing is. Actually, it is O(n), because if these cover the everything, that's N, right? That's N values. If they cover everything, then this one runs once, right? If they don't cover, then it will return here. Yeah, so it is O(n). All right, are there any count modulo? This is good. If I value equal to 0, doesn't exist, and this, oh, this is good. Cleaner. Yeah, definitely cleaner. And I like this way. This is a good way, because at most, right, it will not be larger than the size. But not will be larger than the size. Right? The answer cannot be larger than len nums plus 1. It just cannot, right? It just cannot be, because we can do 0. Everybody if can fill, right? It's just the cannot be larger than this. And we can just and then we don't have to pre-fill the exists set. We just need to iterate through len nums plus 1 and find the first that does not exist. Find the first find the first whose remainder after dividing, after mod value has no count in the RAM counter. So this will still do. Then we just say for I in range len nums plus 1. Actually, it cannot be larger than len nums. If I mod value, RAM counter I mod value. If not, then return I. Otherwise, RAM counter I mod value. I say R, that's fine. Minus equal 1. Yep. This is much simpler. OM. All right, that's it. 1 hour.